Hello guys, welcome to this video. In this video we're going to implement the interrupt descriptor table. The interrupt descriptor table is similar to the interrupt vector table of real mode. It is similar in structure to the global descriptor table, and it basically tells the CPU where the interrupt service routines are. Each entry in the interrupt descriptor table has this form. It has a lower offset, a segment selector which points to our code segment, some reserved bits here, a gate type, we're going to use a 32-bit interrupt gate, a 0 bit, the DPL, which is basically the CPU privilege level which is allowed to access the interrupt. We have the present bit, and then we have the high offset. Here you can see it in a struct that we have defined. It contains the low offset, the high offset, the type, the 0 bit, and the selector. And here we have the IDT pointer. Basically, it will contain the size of the interrupt descriptor table -1 and the base address of the interrupt descriptor table. You can see here that both structs are attribute packed. It means that the compiler will not do any optimization. It will not add any bytes to align the structs. So, before we do it, there are some things we need to do. Some things we need to set up. First of all, we need to create the in-B and the out-B functions. We're going to call them from C. Basically, this one will read 1 byte from a specific I/O port. Basically, we're going to use this function from C to access 1 byte from a specific port. How it works is, we push the base pointer, basically we save it in the stack, and then we move the stack pointer into our base pointer. We clear our EAX register, and then with the EBP +8 we access the argument that we passed in the function from C, and we pass it in the EDX register. Now with the in instruction we read a byte from the port specified into the AL register, and then we pop the EBP. Now I have added here, because someone might not know how the stack works and why we do this thing with the base pointer. Basically, this is how the stack looks if we don't push the base pointer. We have the return address where the function will return to after it finishes, and ESP +4 we have the first argument, and ESP +8 we have the second argument. Now, if we decide to push the base pointer, we have some advantages. First of all, even if something manipulates the stack, adds to the stack or removes to the stack, we can still access the function's arguments with consistent offset, whether it is +8, +12, etc. That means that this is how our stack will look. We will have the old base pointer, the return address, and then we have access to the arguments. The first one will be EBP +8, the second one EBP +12, and then +4, +4, +4 for the next arguments. So, if you have any questions, please write in the comments and I will explain more for you. Then we have the out-B instruction. This one writes information, writes a byte to a specific port stored in the EDX, and we pass the data to as a function argument. Basically, we load the byte to be written in the EAX register and the port number in the EDX register, and then we write the byte from the AL to the port specified in the DX register, and then we pop EBP and we return. We are going to use those soon, so I wanted to explain to you what they do. Then we're going to see what means to remap the master peak. Let's close this, we don't need it anymore. So we have to remap the master peak because there will be some conflicts with CPU exceptions. CPU exceptions are reserved by the Intel architecture until 0x1f. What does this mean? By default, the master peak uses interrupt vector from 0x08 to 0x0f, basically interrupts 8 to 15. But the CPU reserves interrupts from 0 to 31 for its exception handling, like division by 0, general protection fault, page fault. To resolve this, we remap the master peak to start at the interrupt vector but at a higher offset, at 0x20, which is decimal 32, basically one above the last used by the CPU, one above 31. So, how we do that? We clear interrupts, first of all. We don't want some interrupts to be called while we do the remapping. And then we define some constants. Here we have the pick1 command, which basically is the command for port for the master peak. We have the master peak and the slave peak. For now, we are going to set the master peak only. I don't know if we will use the slave peak, but it's open for the future. But for now, the master peak will be absolutely enough for us to use. We have the command for port for the master peak. We have the data port for the master peak. And then we have the initialization control word, which is 0x11. The new offset where we're going to put the master peak. And then the 8086 mode word, which we put in the initialization control word for 8086 constant. So let's start the process. Here we move this constant into the AL register. This basically starts the initialization. After we use the out instruction and we send the value of the AL to the command port of the peak, we basically start the initialization process and it will wait for further instructions. Then we put the offset, the new offset, basically 0x20 in the AL register, and then we send the new offset to the data port of the master peak. And then we set it to the 8086 mode into the data port 0x21 of the master peak. And then we start interrupts again. So this is why and how we do the remapping. Then if we go to the idt.c file, you will see that we have 256 interrupt entries. We define our code segment again. We're going to use it in our code. Here we set up our interrupt descriptor table with 256 entries, and we set up our pointer. Now let's go to the bottom to initialize the interrupt descriptor table. First of all, we set our interrupt descriptor table to 0 using the memset function. The memset function we have already set up here. Where is the memory? Here. We cannot use the standard library now, and these functions we need to define ourselves. So the memset function we have defined in the memory.c file, and we can access it using the memory.h file. I have added some description. I'm sure you know what these two do. We are going to use only the memset now, but soon we will use the memcopy too. So we set everything to 0. The IDT pointer, we set it as to the size of the interrupt descriptor table -1, and the base as the address of the interrupt descriptor table. Now, we initialize the IDT entries with an empty interrupt. What does an empty interrupt mean? It's basically an initialization of our interrupts. What it means is, let's go to our idt.asm. So, this is our empty interrupt. And here we have the empty interrupt handler. What happens here is that we have the empty interrupt, it clears interrupts, it pushes all general purpose registers, and then it calls from C the empty interrupt handler, and we can access it from here. From C, let's see where our empty interrupt is. We set the prototype of the function here. We don't need to set it as external, and the compilation will take care of it for us. And here we can say that all our 256 will be empty interrupts. Empty interrupts means that for now, until we set it as something later, it will just notify the peak that this interrupt has been handled, so it can allow further interrupts. We don't basically want our system to stop. We want, if an interrupt happens and we don't want to do something specific about it now, to tell the system that the interrupt has been handled, so it can go to the next one. We do the same for the interrupt 21 and interrupt 20 handlers. You can see them here. You see the offsets and the interrupts here, but we basically start from 0x20 because we remapped the master peak, which means that interrupt 0x20 is the programmable interrupt timer interrupt. 0x21 is the keyboard interrupt, and it goes on. So what we do is, if we want to see the programmable interrupt timer interrupt running, we basically, and we check the it's 0x20 basically. What we do is we create the interrupt 20 handler, we write something on our terminal, and we signal that the interrupt has been handled. Then we create a handler in our assembly. We clear interrupts, we push all general purpose registers, we call the C function interrupt 28 handler, we pop all general purpose registers, and we start interrupts again. So, and after we do that, what happens is, now that we actually publicize this interrupt 20 handler so that we can access it from C, and then after we set everything to an empty interrupt, 0x20, we say that the handler will be interrupt 28. 0x20 because, as I explained, it's the new offset, not 0. This is the timer interrupt. We will do the same for the keyboard interrupt, which is the next one on the list. How we do it? The exact same process. We have the interrupt 21, it calls the interrupt 21 handler from C, and then we make the function public. It's here. We make the function public, and we have set the prototype up here, and then we set it here. How does this function work, the set IDT entry? Basically, we find the number from our interrupt descriptor table, the 20 interrupt, the 21 interrupt. And what we do is we set the offset low. Basically, we take the handler and we mask the higher 16 bits, so we have the lower 16 bits. For the high bits of the offset, we shift the handler to the right by 16, and then we can skip this actually. The 0, we set it to 0. Now, the type attribute. If you see here, the interrupt gate, the 32-bit interrupt gate is at 0xe. But you can also see it here, 0xe equals to 1110 for the 32-bit interrupt gate. But the present bit is 1. The DPL will have it as 1 and 1, and the 44 is 0. So we have also 1110, which basically means that we can set our type attribute as 0xEE. And then we have our code segment, which is 0x08, and if you remember, we have also set it up in our kernel.asm here. So let's run our code to see. Basically, we will see a lot of messages that say timer runs. Let's try it like this for now. And this is the timer runs. I don't know if you saw that the keyboard was pressed, but let's comment this one. And let's run it again. And here you see that the key was pressed. So we have a lot more work to do in the next videos. We have successfully set it up, the interrupt descriptor table. Thank you very much for being here. If you have any suggestions, if you want something else to see in another video, tell me, and I will do it if it's possible. Thank you again, and I will see you soon.